We're going to talk now about the stagnation point. Now, we saw the stagnation point used when we did the example of the pitot tube. And with the pitot tube, we made the observation that if you had a tube that was facing a flow like this, with the flow coming this way, and this tube was a manometer, at some point, the fluid would stop flowing in the tube as the pressures equalized. And so the velocity right at this inlet had to be zero because there's no more fluid going into that tube, no fluid coming out of that tube. And when the velocity went to zero, that caused a change in pressure based on our understanding of the Bernoulli equation. And we could make that pressure measurement and then compare it to the pressure measurement for a moving fluid and thereby measure the velocity because we know that the pressure is going to increase by an amount related to that velocity squared. So we're going to take a little closer look at that stagnation point and that stagnation pressure to figure out where it's going to occur in other types of flows. So if Z is constant, which is often the case in many of the flows we study, or Z is approximately constant, then we know that as V goes to zero, that pressure is going to increase. So P is going to increase based on this Bernoulli equation. If Z is constant, that's not going to change. As V starts to drop, we're going to see an increase in this P in order to hold that constant value, that Bernoulli constant value. The stagnation pressure is defined as the pressure when that velocity has dropped all the way to zero. So the stagnation pressure is P when V has gone to zero. So if V goes to zero, that's going to result in a maximum pressure increase here. Again, if Z isn't changing, then V going to zero is going to result in the largest increase in P. So that's going to be the highest pressure the flow can attain. And that's called the stagnation pressure. The flow has stagnated. It has gone, the velocity has gone to zero. So we can write that down as P stagnation as a definition here is equal to whatever the pressure is at some point 1 plus rho times V squared over 2. So this is P1 is a place where the fluid is still flowing. And then the stagnation pressure at that location would be this, because whatever the velocity is at that position, that velocity goes to zero, and then this pressure would increase. So every position in the flow has a stagnation pressure. Obviously, if it's following Bernoulli's equation entirely, then the whole system would have the same stagnation pressure because that would all be adhering to the same Bernoulli constant. So this term here, because it has units of pressure, it is called the dynamic pressure. So PV squared over 2, sorry, that's rho V squared over 2, density velocity squared over 2 is called the dynamic pressure. So this is the component of the stagnation pressure that is coming from the fact that the fluid is moving. If the fluid were not moving, then it would have no dynamic pressure, and the stagnation pressure would be the same as its absolute total pressure, its absolute pressure. So this pressure, this dynamic pressure, is the component of the stagnation pressure that comes because the fluid is actually moving. The important thing, however, is that stagnation pressure will only be achieved if V goes to zero without viscous effects, because we know the Bernoulli equation is not valid if there is viscosity. So this is obviously a major limitation. Once again, the Bernoulli equation is an approximation that assumes there is no viscosity. So, and that, of course, is never actually true if something's moving. But the stagnation pressure will only be achieved if V manages to go to zero without viscous effects. Because if there are viscous effects, we know that that will reduce the energy of the system. So viscosity, what viscosity is going to do is it's going to, changing the focus here briefly, see if we can improve a little bit. Didn't really. Try again in a minute. The viscosity is removing energy from the system and dumping it as heat into the surroundings. because that's what friction does. Friction removes energy from systems and puts it into a less useful form in the form of heat. So the stagnation pressure will only really occur if you can manage to get that velocity to go to zero without any viscous effects, any viscous losses. So if you look at a wing where you have the pressure and the velocity out here in the free flow P0 and some V0 flying across, it's the wing flying it through the air, so the effective velocity is V0. Then you can imagine there are a lot of different points where the velocity is zero. I'm going to just label a few points on this wing so we can talk about them. So all of those points are going to have zero velocity, right? Because we know the no-slip condition is a real thing. And the no-slip condition says that anytime the fluid is in contact with a solid surface, we're going to have zero velocity. So there's going to be zero velocity at B, there's going to be zero velocity at C, and there's going to be zero velocity at A. And we know that. And there's certainly going to be zero velocity because of the no-slip condition. But the velocity at B and C, those are only zero entirely because of viscous effects. So there's nothing that causes that velocity to slow down as it tries to fly over the top of this wing, except that it's got viscous effects. The wing is not moving, and so that the air friction between the non-moving wing and the fluid right above it is causing that velocity to go to zero. So the pressure at B is not going to be stagnation pressure. The same thing is true of C. Again, the only thing causing that fluid to slow down is viscosity. Otherwise, it would just flow right by, scooting right along the under edge of that wing. So that would have the same velocity as the free stream, this V0, unless there's viscosity. But viscosity is going to drag that velocity down to zero. So the velocity, the pressures at B and pressures at C, PB is going to be actually equal PC. They're actually going to be P0. We're going to show later in the class that the flow won't support a pressure difference between up here and down here. So the pressure up here is P0. So this is going to have the same pressure as this. It's going to all be atmospheric pressure. So there's not only is the pressure not a stagnation pressure, it's actually not even any different than the pressure far from the wing. So those are definitely not stagnation points. Point A is a stagnation point. So why is point A a stagnation point? Stagnation here because it's not viscosity that's causing the flow to go to zero pressure here. It's the fact that there's an object directly in the way. And that's going to cause a pressure buildup in front of the wing. So the fluid is going to slow down and actually go to zero velocity at this point solely due to pressure effects, or primarily due to pressure effects, I should say. There, of course, are some small viscosity effects, but the effect at point A is primarily a pressure effect. So PA is going to equal stagnation pressure, and that's the only point in this flow that's going to have stagnation pressure. If you have a large, the front of the wing actually would look something like this. You would get true stagnation pressure right at that point that's really, really almost perpendicular to the flow. Up here, you'd have some combination of pressure and viscous effects. Up here, maybe a small pressure component. Mostly it's viscosity. Here, it's going to be all viscosity. So this is going to be not any stagnation pressure here. This is going to be true stagnation pressure. This is going to be something in between.